For this lecture, I'm going to give you a 5-minute summary on the second law for closed systems using entropy, and then we'll just work some examples. So I'm going to talk about the entropy generation concept. The textbook will use entropy generation or entropy production simultaneously, they mean the same. Let me go back just a little bit to set this up. We were actually able to derive an inequality that applies to a process going from a state 1 to state 2 by using the Clausius inequality that applies to a cycle. So this is an equivalent statement of the second law. The integral of a cycle of dq dt is less than or equal to 0. Well, we considered a cycle that goes between state 1 and 2, a process A, irreversible, 1 to 2, and then the return process 2 to 1. So for the internally reversible case 2 to 1, we can replace that integral with the change in entropy, right? S1 minus S2. So in the end, we were able to convert that Clausius inequality to show that the change in entropy between two states is always greater than or equal to the integral of dq over t. And then we can also postulate, or actually it is true, that this, take the limit as s approaches, as 1 approaches 2, this actually occurs on a differential rate basis as well. So ds is greater than or equal to dq over t, and then divide by time, and then on a rate basis ds d time is greater than or equal to, now turn this into a rate, q dot over temperature. So all of these hold and represent another equation or inequality of the second law. So let's start with this inequality and use that to provide a basis for the entropy generation concept. All we're going to do for the entropy generation concept, take that take that inequality, applies to any closed system. And what we're going to do is we're going to add a quantity to that, sigma. In this case, it's a differential amount because all of these are derivatives, differential quantities. Add just enough to force that inequality to become an equality. And then if you integrate this between states 1 and 2, this is an equation for the energy balance. S2 minus S1 is equal to integral of dq over t plus this sigma term. This is entropy production or entropy generation. This is entropy change due to the fact that the material is moving from one state to another state, and this is entropy generated at the boundary due to that irreversible heat transfer. Remember, heat transfer has to be an irreversible process. So this is effectively evaluated. The textbook will put a little b there. That's evaluated at the boundary. So you kind of need to know what's going on with the temperature as a function of time in this interval at the boundary. So this really needs to be an integral to be most generally represented as an integral over the entire, a surface integral over the entire boundary. Okay, so if sigma is 0, then we have an internally reversible process, right? If this is an equality up here, then this must be internally reversible, definition of entropy, if you guys recall. If sigma is positive, then this will be larger on the left-hand side, and then we have a possible process, theoretically possible according to the second law. If this is negative, then that would violate the second law. That would suggest that this is negative. I'm sorry, this is less than 0 up above and would violate the second law. So now we have a means of evaluating the second law. Use this entropy balance equation, solve it for sigma, and then check the sign of sigma. Sigma is positive, theoretically possible, irreversible device. If it's equal to 0, then we have an internally reversible process, so the theoretical limit effectively. If it's less than 0, then that violates the second law. So it's sigma or entropy generation that you use to check the second law, not the entropy change. Now sometimes the entropy change is coincidentally equal to sigma, the entropy generation, but it's the entropy generation that actually allows you to evaluate the second law. Okay, so to use this equation in this form, we need to know something about the temperature of the system, and what in particular at the boundary. So we have to have some means to evaluate this. So to help alleviate that, because we can't always evaluate this, what we can do is apply this concept to an isolated system. If it's an isolated system, then there is no heat transfer. Q is gone, and so delta S is actually equal to sigma. So I have ISO here to suggest that it's isolated. So we can think of the system plus all the immediate air, right, gas around the system, as a thermal reservoir is the air around the system. So if we add the system plus the immediate surroundings, we can think of that as being isolated. Therefore, all we really need to do is evaluate sigma isolated. So sigma isolated is also actually called delta S total. You have the entropy change for the system, but also the entropy change of the surroundings, and the surroundings would be a thermal reservoir. So the heat, so they are isothermal. The temperature is not changing for surroundings, and so it's internally reversible. So for the surroundings, this is 0, and so delta S for surroundings is actually dq over T, and T is isothermal, so it comes out front. So after you integrate, it's Q over T. So we need Q surroundings over T surroundings to take care of the entropy change for the surroundings. And so that's what this is, Q surroundings over T surroundings, except that Q surroundings is negative Q of the system. Whatever is going out of the system is into the surroundings. Those are in opposite signs. So we can use this as well as checking the second law. And the value of this is that we only need to know the temperature of the surroundings here, not the temperature of the boundary of the system, or the temperature even of the system, to evaluate the second law this way. So we can evaluate the second law with sigma isolated, which isolated means sigma of the system plus of the surroundings, and we would use this equation. If you have a means, if you don't know the temperature of the surroundings, for example, and you have a means to evaluate this integral dq over T at the boundary, then this will suffice to evaluate the second law. Okay, so second law for closed systems using an energy balance. Let's work some examples. I didn't mean to show you the solution yet. So this is one of your homework problems. I'm starting with the homework problems that are applying an entropy balance. And so there are several of your homework problems that just have you evaluate entropy. I'm going to let you do that on your own, get practice with that, and ask me questions during our Zoom session. So problem 635 is a piston cylinder assembly. There's water inside this. They give us information about a state 1 and a state 2. It's going through a constant pressure process, and it's starting off as a vapor, saturated vapor. They're cooling it off, so heat transfer is coming out until you have all saturated liquid. So we're just going straight across the wet dome at a constant pressure, right? So that connection being constant pressure under the wet dome means that the temperature is going to be the saturation temperature, and it's going to stay constant as well. So kind of not explicitly given, but that's what's going on in the problem. So in the tables A3E, I think it is, they actually give us one row that corresponds to 1 atmosphere, 14.696 psi. So use that column, sorry, that row in the table. So T saturation at that pressure is 211.9 degrees. This is Fahrenheit. So we're going to convert that to degrees Rankine right away. Evaluating the second law is kind of crucial to sigma. Can be a very small number, maybe a little bit positive or a little bit negative. So it's important to keep 5 digits of accuracy here. So don't use 460, use 459.67 when you convert, and keep 5 digits of accuracy in all your temperatures. So this question now, let's go back, is asking for Q. What's the heat transfer out of the system to make this happen? And then what is the entropy produced? So we need to come up with sigma for the system. Okay, so we can do I'm going to go ahead and write from here. and then we can just check the answers. Let's do a first law to come up with Q. For first law, Q minus W is equal to, I'm going to put mu2 minus u1, so this is delta U. We would also have a kinetic energy and a potential energy term that we're neglecting. So I'm going to show that and neglect that. That is delta U. So that's like effectively stating the assumptions here that I'm neglecting those changes. This is the integral of P dV, which in this case pressure is a constant, so that's just going to be P1 V2 minus V1, and if we factor out an M out of this, that's M V2 minus V1. And so if you remember, we worked one example with a constant pressure process in which we took this term over to the other side and we combined the work with the U term. So let's do that. I'm going to substitute this in and take that to the other side. We're left with Q is equal to M U2 minus U1. That's a minus here. It goes to the other side. It becomes plus. So plus P1M V2 minus V1. And so now these two properties can be combined to enthalpy, right? U plus PV is enthalpy. So this is actually just MH2 minus H1. Okay, so H1 is Hg, H2 is H. At the end state, we end up as a saturated liquid. So we can substitute in numbers for that and come up with a value for Q. So that's what I've done here. Here's our two H values. If you go to the table, keep all significant figures here. They give you 5 digits, keep all 5 digits. 1150.5 for Hg, for Hf 180.15. This ends up equaling minus 970.35 BTUs. So this is negative, and so it's out to cause the vapor to condense and end up as a liquid. So that actually makes sense. Now let's start thinking about the second law. For the second law, we'll write it out as an entropy balance. S2 minus S1 is equal to the integral from 1 to 2 dq over T at the boundary plus sigma. Okay, so for this process, the temperature is isothermal, so that's a constant. All right, that's isothermal. T1 equals T2, that's T saturation at the pressure. All right, so that's this 671.66 degrees Rankine. Okay, so if that's isothermal, then that can come outside, and if you integrate dq, then you're left with Q. And that one is MS2 minus S1. That's just the entropy change for the water. Okay, so we're left with, let's solve this. Sigma is equal to MS2 minus S1. This goes to the other side, so minus Q over the temperature, T. I'm just going to put T1 there. Alright, so that is T sat again at the pressure. The pressure is constant for the process. So both states are defined, so we can evaluate those S values, and then that we've already calculated what Q is. So we can solve for sigma. So now let's look at the results. There's the expression for sigma. S1 is Sg, S2 is Sf, saturated liquid value. There's my temperature, isothermal, and there's the heat transfer. So that's a negative Q, right? That negative Q goes in place here, so you'll end up with a negative and a negative that cancel. Okay, so if we substitute in, this is S2, which is the SF value, S1, which is the Sg value. So this ends up equaling a negative number times the mass. It's 1 pound mass. Okay, so this is the Q, so there's a minus, because Q is a minus number. So those two minuses are going to cancel. Pound mass cancel in this term, so we're left, and both terms are BTUs per degrees R. So this is a wrong. Finally, that unit is wrong right there. That is a degrees Rankine in the denominator there. So this, notice that this is a very, very small number, but it is a positive number. So this is very close. You might argue an internally reversible process, but it is satisfying the second law. Very, very close to the boundary. So almost effectively an internally reversible process. I think the textbook solution manual actually calls it internally reversible and calls that 0. But once again, sometimes sigma can be that small and be a negative number, in which case you're going to have to say that it is theoretically impossible, at least based on your calculations. Okay, so once again, keep several digits of accuracy there. So that's all for that problem 35. I think that's all they were asking for. So this satisfies the second law. Okay, let's move on to, well, actually there's more to this problem, isn't there? I should have had the problem statement. So it also wants us to calculate the entropy of the composite system, or this is still continuing with this problem number 35. It also wants us to calculate the entropy generated considering the system plus its immediate surroundings, which we're going to treat as a thermal energy reservoir. So the system itself plus all the air surrounding it. They're saying that the air is at 80 degrees Fahrenheit. We're going to treat that as a thermal reservoir. So even though there's energy coming out of the system into this air, right? So the air is actually technically increasing in temperature the tiniest little bit. We're going to assume that that's negligible and assume that this is an infinite thermal mass effectively. So a thermal reservoir that remains at a constant temperature. So now let's evaluate the entropy change of the composite system. So delta S of the composite system, so the system is all of this together. So way out here on this boundary, we're going to assume that that's adiabatic. So we're going to apply the same equation before, S2 minus S1 for both of these now, right? I have the entropy change of both components of this composite system. There's no heat transfer out on this outer boundary. And so I'm going to go ahead and call this isolated because this is the concept we generated before for an isolated system. If we include the thermal reservoir around the system, that's an isolated system. Okay, but the delta S becomes delta S of the system plus delta S of the surroundings. All right, so this is for the system. We know state 1 and state 2 and the mass, so that can be calculated fairly easy. For the surroundings, though, the surroundings are actually equal to Q of the surroundings divided by the temperature of the surroundings, because it's an isothermal system. We're evaluating dQ dt for the surroundings, assuming it's internally reversible. So we've talked about the theory of this before. And then we'll just recognize that Q surroundings is actually minus Q system. So we can actually substitute minus Q system, the Q that we've already computed, divided by the temperature of the surroundings. So but this quantity here, that replaces S2 minus S1 surroundings, M S2 minus S1 for the system. So here's what we're left with. Sigma isolated is M S2 minus S1 minus, and the minus are going to cancel again. So this looks just like the calculation we just made on the previous page. When we knew the boundary temperature, we had actually temperature of the boundary here. Alright, but now we're going to replace that with temperature of the surroundings, and now instantly we are now computing sigma isolated rather than sigma of the system itself. But sigma isolated still needs to be greater than or equal to 0 in order to have a theoretically possible process. Okay, so now if we recalculate this with temperature of the surroundings here, this number is much larger. And so there is entropy being generated or produced. So this is a physically possible, irreversible system. Let's say theoretically possible, irreversible system. So there's sigma isolated. I actually prefer that we check the second law with sigma ISO, because it's not common to actually have a boundary temperature. It's very common to know, well, what's the room temperature, right? With just a thermometer, what's the temperature of the air around the device? So this is a much more convenient, I think, version of this, but you have to use whichever equation is needed based on the information they give you in each problem. Okay, so finally that does conclude 635. So now let's talk about problem 643. Okay, so here's the problem statement. We have air in a piston cylinder assembly. They're telling us that it's adiabatic. It's going through a compression. Low pressure, 1 bar, it increases to 10 bar, and the temperature also increases as it is being compressed. So it's adiabatic, so they're not letting there be any heat transfer, but there's just work that is applied through the piston. So they're asking us to find what is the entropy produced per unit mass of air, so really sigma over m. But you know, m, mass, is always a positive quantity, so you can actually use sigma over m also to evaluate the second law. Sigma is greater than or equal to 0. Sigma over m is also greater than or equal to 0. And then they're asking us to get the minimum work required to achieve this compression. So the minimal amount would be if we had an internally reversible process, right? That would imply that we had no losses if it's internally reversible. So nothing like friction or other irreversibilities that would cause the energy to be effectively lost going somewhere besides into the work of the system. This would actually go into probably heat transfer. Okay, so to calculate the minimal work, we actually can't integrate PdV. And the reason is we don't know what's going on throughout the process as we go from 1 to 2. We don't know how P varies with specific volume. We don't have that function. So we're going to actually have to use an energy balance. So I'm going to go ahead and write it out like last time and then show you. Alright, so we're going to do a first law. Q minus W M U2 minus U1 plus delta kinetic energy plus delta potential energy. We'll cross those out. States 1 and 2 are defined, so we have both of those. It is adiabatic, so we'll cross that one out. We'll take this M and divide through because we're evaluating things on a per unit mass basis. So let's take that, divide through by M, and then I'm also going to take that minus sign to the other side. So little w, right, which is defined as W over M, is going to end up being U1 minus U2. So both states are defined, so we can actually calculate a U1 and a U2 that will give us a value for that work. But this will be the actual work for the process, not the minimal work for the process. So this is the actual work that was input to get us from state 1 to state 2. So we can substitute in numbers for that. I see I have that right here. Substitute numbers for that. This is U1, that's U2. So our work, actually, is that right? U1, that's U2, and that's U1. I think I have this sign swapped on that. Our work for this compression process is actually an input, so that should be a negative number. I think these are backwards. Those are backwards, and that, our work for this compression, should be negative. So that should be a negative. Right there is a negative, and so my U1 and my U2 are backwards for this. Right, now it is air. That's all I can tell because it is air. Use only a function of temperature. So the lower temperature, right, would be a lower U. The higher temperature would be a higher U. So I definitely have those backwards. Okay, so it's going to be the same answer with a minus sign. So it's minus 220.7 kilojoules per kilogram is the actual work required to take the system, the air, between these states 1 and state 2. Now we before we do the minimum case, let's think about what's going on to the second law, because for the minimum, basically, to make it an internally reversible process, what we're going to do is use the second law to evaluate what internally reversible is. So let's think about the second law for this. I'm going to go ahead and just show you. Start with the entropy balance. S2 minus S1 is equal to the integral of dq over T plus sigma generated. It's an adiabatic process, so this term is actually gone. So for an adiabatic process, delta S is actually equal to sigma. So this is actually M times S2 minus S1. Right, if I divide through by this M, sigma over M is equal to S2 minus S1. And now to evaluate for an ideal gas, the entropy change, right, I have to evaluate that with the equation that we have for an ideal gas. Standard state entropy change minus R natural log of P1 over P2. Remember, I told you for an ideal gas, you'll never calculate an S1 or an S2, just the change. So we're going to substitute that equation for the change. The standard state entropies depend on the temperature. So S2 depends on the temperature, S2 naught, S1 naught, both of those depend on the temperature. You can go to the tables and come away with those. You need to go into the tables with absolute temperatures. So temperature 1 and temperature 2 give us that. We need R for air, 0.28699, so this is 8.314 divided by the molecular weight of air is 29.96, I think. You'll have to look up what that is. But again, when we evaluate sigma, it might end up being a small number in the end. So we need to keep many digits of accuracy here. So keep 5 digits of accuracy. I wouldn't even stop. Actually, it's probably not going to make a difference to do 0.287. Since it happens to be so close, you're hardly rounding up to make that happen in this case. Okay, so all of these numbers can be substituted in this above, and that gives us entropy production over the mass now is equal to 0.046171. So that's a positive number, right? So this satisfies the second law. This is an irreversible process that takes you from state 1 to state 2. Okay, so to find now, this is kind of a important concept here that's not really revealed in the problem statement. To find what we're going to call the theoretical maximum amount of work, minimal amount of work required to make this happen, what we're going to do is we're going to relax the temperature at state 2. So we're going to assume that the temperature, we still start at 300 K, but we're not going to end at 600 K, right? So, well, it'll be something less than that. So what we're actually going to do is we're going to say, let's figure out for a reversible process what the temperature would be at state 2. So it's not going to be 600. Instead, we're going to call that T2 minimum. But I'm going to put a little subscript S on here to identify that rather than being the T2 actual that they give us, this is our theoretical T, or the minimum T. Put a little subscript S. S is referring to entropy because we're going to assume it's an isentropic process to get to that T. Okay, so now let's apply the entropy balance, S2 minus S1, integral of 1 to 2 plus our sigma. And then let's go back and postulate for the minimal temperature at state 2. We're going to assume internally reversible. If it's internally reversible, there is no sigma. Right, so we're crossing out the sigma. It's adiabatic, so that term is gone. So what we're left with is to say S2 minus S1 equals 0, which means there is no entropy change. It's an isentropic case. And once again, instead of calling that T2, I'm calling that S2, I'm calling that S2S. Instead of 2, it's 2S to identify that state because it's our theoretical isentropic state. Okay, so now replace this with M times S2S minus, that's supposed to be an S1, minus S1 is equal to 0. We're going to evaluate the entropy change for an ideal gas as standard state entropy change minus R natural log P2 over P1. So this is actually a 2 S there as well. So this is equal to 0. Well, take a look at everything we know here. We know the pressure at 1 and 2. We know the temperature at 1, so we can come up with that. We don't know the temperature at 2S. Right, so we can use this equation, solve for T2S. Go into another page now. Right, here's the same equation, S2S minus S1. Substitute in for the ideal gas evaluation of this. This is equal to 0 to make our T minimal or isentropic case. Take these two to the other side of the equation. We're solving for S naught 2S. Right, so we have the temperature, so we have a number for that. In fact, we've already used it, right? We've already looked that up. We already have an R. So this comes out to be 2.32628. So keep all 5 significant digits there. Now we can go through the tables and look for this under the standard state entropy column and come away with the temperature. It comes out to be 564.1 K. So notice that that is less than the 600 K previously. So what happens in the actual process is that the irreversibilities and the friction actually causes a little bit of heating, which raises the temperature above the theoretical minimum that would occur for a reversible process. Okay, so we also, now that we know standard state entropy here, we can interpolate to come out with T2S. We can also come up with the internal energy U2S. So that's 407. And now use this as our state 2. Instead of U2, we're going to use U2S. And so we'll end up with W minimum is equal to, this should be a negative again, equals that. So instead of previously we had the 220, make that a minus. Instead of the 220 input for the actual case, we ended up with 193. So with no irreversibilities, with no irreversibilities, it takes less work. But the actual process that they proposed, the actual work being less than, it's the work that is, it's an input. The actual work on a magnitude basis, let's do that, being greater than that, right? We have to put more input than this minimum means that it satisfies the second law. So this is a theoretically possible process. So for this problem 43, the interesting discussion here, if you're going to make comments about this problem, is this part when it says to come up with the minimum work. We have to know that it's the temperature that we're going to relax so that we can apply a restriction that it be internally reversible and so isentropic. And then we calculate a new T2 and then a new amount of work for the reversible case. Okay, so the last problem that we're going to talk about is, I'm going to skip a couple of problems because they're kind of very similar to what we just looked at. Let's look at problem 651. If you go through the problem statement, it is rapidly heated or cooled. And so when it says rapidly, we're leaving the equilibrium assumption, quasi-equilibrium assumption. So that basically it's telling you that, hey, this is an irreversible process when it has an adjective like rapidly. So in this problem, we have propane. Propane starts at a given state, a pressure and a temperature. And so the pressure is reduced and the temperature is also reduced, so it's probably going through an expansion. We could check the specific volumes of both of those. I'm very certain it's going through an expansion. And so it's being heated as it's going through this expansion. It's giving you, in this case, the temperature of the boundary, right? So we'll use that to evaluate that integral of dq over t term. And it's saying for this process, the work measured is 42.4 kilojoules of output work as we go through this expansion. So the question they're asking is this work theoretically possible? Could that possibly be the correct work measurement? I've gone and looked up these two states. It turned out that they're both superheated. So we're in the superheated region throughout the entire process. Okay, let's think about this a little bit. First, let's just write down the equations. The first law, Q minus W equals M, U2 minus U1, neglecting kinetic and potential energy changes there. Both states are defined. We have a mass associated with this. And so they've got a measured work that we could put there and come up with a consequential Q if that measured work were correct. If we look at the second law, though, we'll do an entropy balance. M S2 minus S1 is the integral of dq over T plus sigma. Okay, since we have the temperature at the boundary, right, we can evaluate this as Q over temperature at the boundary. So we can make substitutions for those. M S2 minus S1 equals Q over TB plus sigma. Both states are defined, right? So we have an S1, an S2, and an M. And we have a temperature of the boundary. We don't have a Q, and we don't have a sigma. And so now the question is, between these two constraints, how are we going to assess the second law based on the measured W? So there's really two ways that I've thought to do this. We could eliminate Q between these two equations up here. So we can take this equation for the first law, solve that for Q, right? Take that Q, substitute it here, and now we will end up with a single equation for sigma. We can compute a sigma that would be the end result should that measurement be correct. And then we can just check the sign of sigma. If it's positive, then it's a theoretically possible measurement. If it's negative, then no, it's not possible. Or another way to do this is to start with the second law. Take this expression and let's take the best possible scenario and assume internally reversible, cross this out, and then use this equation to come up with a Q reversible. So Q reversible would be equal to TB times delta S. And that, right? And all this over here is known. Right, just take TB to the other side. Everything's known. We can solve that. We'll make this Q reversible if we make that 0. Right, so now we can take that Q reversible, substitute into the first law, solve this for W, and that'll give us a W reversible. Alright, so we could compute sigma equal to 0. That'll provide Q reversible. Put that in the first law. That'll give us a W reversible. And then we can compare the reversible case to the measured case. Right, and so the measured cannot be greater than the reversible case. Otherwise, it's violating the second law. So that's how you would assess whether or not it's physically possible. I'm going to let you finish. You have some answers. I think I gave you numerical answers for that. So rather than giving you more details on that, I'm going to let you finish after we've now talked about the logic. My first thought when I was going through being a mechanical engineer would be to figure out what's the reversible work and do a direct comparison of the work. But I got to admit, it's kind of tricky to decide, well, which way is it supposed to be at the end? Which is supposed to be greater than the other that's going to make this permissible? And so that being the case, if you do it the first way, you know sigma. There's no question on that. Sigma has to be positive. Right, so you don't have to worry about your intuition and mechanical understanding being correct, knowing that this is an expansion for this comparison. So that being the case, although I would have done it without thinking, I would have done option 2. I'm going to suggest option 1 because it leaves you no opportunity to misinterpret the second law. Just use sigma has to be greater than greater than or equal to 0. Okay, so I'm going to stop here. We're almost 40 minutes into this, and I think this is going to conclude the second law discussion for closed systems. There's one more topic to talk about, and that is for open systems. And after our Zoom session today, I'll see where you guys are at to see how far and how I want to handle that last topic.